Most national household surveys have three complex sampling design characteristics. 1. Stratification, choosing an independent sample in subnational geographic areas. 2. Multistage cluster sampling, first sampling communities, then sampling households, and sometimes sampling individuals within households. 3. Oversampling, ensuring there are a sufficient number of rural and urban households to estimate national indicators. Together, these design characteristics bias the mean estimates and introduce variance, which is why we have to account for complex sample design when performing survey data analysis. This video will review each of the sample design characteristics and their impacts on the mean and variance estimators. Learn how to account for complex sample design characteristics in the video called Survey Analysis and Stata. Stratification means that survey implementers divide the country into mutually exclusive, exhaustive subnational regions, and then select independent samples within each subnational region. The purpose of stratification is to produce representative statistics for subnational regions, and to be able to compare indicators across subnational regions. Stratification can bias national mean estimates when populations are different in each subnational region, and these subnational regions have different population sizes. Why? It has to do with the fact that approximately the same number of households are sampled from each stratum, but the stratum have different population sizes. Let us think about the impact of stratification through an example. Let us say we are going to select a stratified sample in Rwanda, and we stratify by Rwanda's 30 districts. Here are the total 2010 population figures, in thousands, where dark colors represent larger populations. Kigali district has nearly twice the population as Karehe. So if we sample the same number of people from each district, people from Karehe would be overrepresented in the national sample, and people from Kigali would be underrepresented. We account for stratification by weighing the observations in a given district by the ratio of proportion of district population represented in the sample versus the underlying population. For national estimates, stratification can slightly improve the precision of estimates if the outcome follows a geographic pattern. For example, if we are estimating the percent of women in polygamous marriage, and polygamy is practiced mainly within one region. This is because there is less variation within a given region compared to the country overall. For example, say a country has 6 strata, and each strata has less variation within than the overall sample. Then we could generate an estimate at the national level with more certainty than if we had selected a simple random sample nationwide. Multistage cluster sampling means that we sample increasingly smaller embedded units. The classic examples of students embedded in or clustered in classrooms, and classrooms which are clustered in schools. A multistage cluster sample of students might first list all of the schools in a study area and randomly sample a few schools. Then within the sampled schools, list all classrooms and randomly sample classrooms. If we stopped here and conducted a survey of all students in the sampled classrooms, then we would have performed a 2-stage cluster sample with schools as stage 1 and classrooms as stage 2. You might be wondering why this is not a 3-stage cluster sample design, since students are clustered in classrooms and we ultimately survey students. The reason is we do not sample the students, we take a census of all students in the sampled classrooms. Therefore, the sampling stops after 2 stages. A 2-stage cluster sampling design is used to sample women in the demographic and health surveys, multiple indicator cluster surveys, and other similar household surveys. Within strata, all enumeration areas from the last census are listed and then sampled. In sampling terminology, we call the selected enumeration areas clusters, or primary sampling units, PSUs, since they are units of the first stage sample. Within PSUs, all households are listed and then sampled. We call these secondary sampling units, SSUs, since they are the units in the second stage sample. Then a census of all eligible women is performed within the sampled households. Similar to our classroom example, we describe this sample as a 2-stage cluster sample with enumeration areas sampled in stage 1 and households sampled in stage 2. If we randomly sampled 1 woman per household rather than interview all eligible women, This would become a three-stage cluster sample design. Here is another question you might ask. Most household surveys are stratified by district or province, resulting in non-overlapping geographic areas. Why doesn't the DHS consider strata as a level of the multi-stage cluster sampling frame? Think about how many strata get sampled. All of them, right? Since we have a census of strata, strata are not considered a stage in the multi-stage cluster design. How are means and proportions affected by multi-stage cluster sampling? They are not affected at all, actually. Clustering does not affect means, only variance. Let me demonstrate this. Let us say that we are estimating the highest level of education among women in the Rwanda 2010 DHS sample. Whether we correctly specify the two-stage cluster design with a survey set statement, or run statistics without specifying the two-stage cluster design, the mean proportion of women at different levels of education remains the same. Cluster sampling only affects variance estimates. This is because people from the same community are often similar in some way. For example, my neighbor is more likely to have a similar socioeconomic status and occupation to me than a stranger living elsewhere in the country. Likewise, patients who attend the same clinic are often similar in terms of socioeconomic status and health risks, and think about how similar children from the same classroom are in terms of age and socioeconomic status. When we sample multiple people from the same PSU, we are getting less information about the population than if we had sampled people randomly from across the population. Does that make sense? Remember from the simple random sampling lecture, variance of a proportion is calculated as the prevalence estimate times 1 minus the prevalence estimate, all divided by the sample size n minus 1. The variance estimates from a cluster sample are comprised of two pieces: variance within a cluster and variance across clusters. As you can see, the calculation of the variance estimator for the clustered samples is complex. Conceptually, this variance estimator is discounting information from each additional person that is sampled within a PSU, because people in the same PSU are expected to be similar and therefore contribute less new information to the sample than if we had sampled a random person from the population. If you do not account for clustering in a multi-stage cluster sample, your confidence intervals will be incorrectly too narrow and you will risk finding differences among subgroups that are not real. We call this a type 1 error. You must absolutely account for clustering when performing descriptive statistics with survey data. There is some debate about whether it is necessary to account for clustering in multivariate analysis, which I will discuss when we cover logistic regression. The design effect compares the variance under one sample design with the variance of a simple random sample. To calculate design effect, simply divide the variance, calculated with the survey design, by variance assuming simple random sampling. A design effect larger than 1 means that the variance under the sample design is larger than it would be under simple random sampling, and a design effect smaller than 1 means that the variance under the sample design is smaller than it would be under simple random sampling. The design effect of a complex survey design is usually reported by survey implementers for key indicator variables, and is helpful for sample size calculations in future surveys that use complex survey designs in that population. In large household surveys, samples are often designed to ensure that a minimum number of respondents are selected from important subgroups, so that robust estimates and comparisons can be made across subgroups. Urban and rural populations are usually considered the most important subgroups. In low-income countries where the overwhelming majority of the population is rural, oversampling is commonly performed in urban populations by sampling extra PSUs in cities. Oversampling changes the probability of selection. If urban areas are oversampled, then individuals living in urban areas have a higher probability of selection than individuals living in rural areas. Oversampling biases the mean estimates. For example, access to formal education is usually higher in urban areas. If we oversample urban people, then the proportion of urban people in the sample will be greater than the proportion of urban people in the population, and our estimates will be biased. They will not represent the population. Going back to Stata, if we estimate highest level of education among women in the Rwanda 2010 DHS by correctly adjusting for sampling weights, and then we estimate the same variable without sampling weights, the unweighted estimates incorrectly show women to have higher access to education than actually exists. A key principle of sampling is that everyone in the study population has an equal probability of selection. When there is unequal probability of selection, we must A, know the probability of selection among respondents, and B, incorporate these probabilities into our analysis using sampling probability weights. As with other aspects of complex sample design, probability weights must be used in descriptive analysis of means and proportions, and there is debate about whether oversampling must be accounted for in multivariate analysis. Oversampling in household surveys usually entails the addition of a few extra PSUs. If these PSUs are sampled randomly, in other words, everyone within the subgroup has an equal probability of selection, then oversampling does not affect variance estimates. The only way that the variance could be affected is if the overall sample size is increased by adding PSUs, in which case the effect on variance is the result of increased sample size, not of oversampling. Response rates can bias mean estimates if certain kinds of people systematically refuse or are not available to participate in the household surveys. If, for example, interviewing is performed at a time of day when women farmers tend to be away from the house working in the fields, and interviewers are more likely to encounter sick women than healthy women, then the sample is not representative of the population. Although we do not know the characteristics of the women who were not interviewed, we can calculate the probability of selection among those women who were interviewed and adjust the contribution of their information to our mean estimate. Sampling probability weights adjust for unequal probability of selection introduced in the sample by stratification, oversampling, and unequal response rates. If we are analyzing a national household survey like the DHS, then sampling probability weights will have been calculated for you and provided in the dataset. The sampling weight is equal to 1 over the probability of being sampled, or 1 over small n divided by big N. You will remember from math class that this can be rewritten as big N over little n. The sampling weight is applied to each observation when estimating prevalence. Notice that the denominator of the weighted estimator is big N, the total population. This is different from the unweighted estimator presented in the simple random sampling video where the sample size little n was in the denominator. Another way to think about the unweighted estimator is that it has a constant weight, an equal probability of selection for each person in the population. The estimators are equivalent, and this is how we get from the weighted estimator equation to the unweighted or constant weight estimator equation. The weight, big N over little n, can be pulled out of the sum operator because the weights are equal to 1 for all individuals. Then the big N's cancel out, and we are left with the sum of the indicator y across all sampled individuals over little n, the sample size. Several characteristics of complex survey design can bias mean and variance estimates. Any survey design characteristic which affects the probability of selection, including stratification, oversampling, and response rates, must be accounted for with the application of sampling probability weights in descriptive data analysis. Descriptive data analysis must also adjust for clustering by widening the variance estimates to avoid making type 1 errors. Accounting for stratification can slightly narrow confidence intervals and analyses of multiple strata, but the effect is usually negligible, and so the effect of stratification on variance can be ignored in descriptive data analysis. I would like to acknowledge that this presentation was based off of learning materials developed by Dr. Bethany Hetgothier. Go to populationsurveyanalysis.com for a PDF version of this video and other learning materials that support your analysis of a population survey dataset.